Now today we are going to look at the physics problem. We are going to solve a time-independent Schrodinger equation in one-dimensional infinite potential valve, a particle in a box, numerically, given that the potential from 0 to L is 0 potential and infinity at the site. And you know that the Schrodinger equation in this region can be simplified by this one. And your task is discretize the spatial domain x from 0 to L into n points and construct the Hamiltonian H using finite difference approximation for the second derivatives, and then use this NumPy library to find the eigenvalues and vectors, and then plot the first three energy of the eigenfunction of what you get, and then verify the result obtained numerically are the same with the one obtained analytically. So before we start, we want to introduce you understand what is finite difference method. Okay, finite difference method is a method to find the gradient. Okay, for example, the derivative of function fx is equal to this equation where h is very small, so it becomes a gradient. And for second order derivative, it can be given by this equation. So the finite difference approximation of the second derivative of the wave function can be given by this equation, okay, where phi I sine I is the at the index I, -1 is before and +1 is after, and this is the second derivative of index I. So you are discretize the distance from 0 to L into n point. So when you can create a Laplacian matrix, okay, delta x squared, which is the here, okay, the -2, 1, and 1. Okay, -2 represent the -2 sine I. 1 here is sine I -1, and here sine I +1. So this from a Laplacian operator, and here with the wave function. So let us look at the solution. So for constant, I use a reduced Planck constant and put mass ml as 1. Okay. Number of points, spatial discretization is 1000. So x would be 0 from L. X consists of an array of 0 to 1000. And delta x is the distance between index 1 and index 0, which is your spacing. So I need to define the operator, kinetic energy operator. Here np full n -2 means that I fill out the matrix of size n with 1D array with -2. And off diagonal are defined as 1D array, okay, filled with 1 with only n -1. Okay, we will explain to you later why n minus 1 here. So Laplacian can be defined as, these are 1D. So you can create a 2D by using this one. So this create a two-dimensional matrix with a diagonal of -2, filled with diagonal -2. And here off diagonal -1. Okay, off diagonal. Okay, -1 means is filled below the diagonal and 1 is above the diagonal. What does it mean? Okay, this is -2 diagonal with np dot diagonal over bracket diagonal. That's what you've created. And -1 here off diagonal is all filled with 1, and you got n minus 1 1D array. 1D array, it becomes 2D by np diagonal. So you have -1, you have a n minus 1 because here you only n minus 1 only rather than n. Same here also, n minus 1 element of 1. Okay, so let's look at a bit of detail. So if I run this np array is 1D 2 2 2 2, so np dot diagonal then have a -2, and if I do -1, so you see you feel just below the diagonal. So now I can create the Hamiltonian. Okay, h bar square 2m times the Laplacian. Okay, second derivative. I then solve the eigenvalues problem. NP, which is described in the question, using this to find eigenvalues and eigenvector. So eigenvalues are eigenvector. When you look detail, okay, you have two objects, 1D array eigenvalues and 2D square array of the corresponding eigenvectors. And you can see there's an example. Okay, eigenvalues, eigenvector. Okay, got eigenvalue 2, got eigenvector 2 times 2. Okay, it's important that we have 1,000 points. Okay, which means that we have 1,000 points of eigenvalues. And we're going to look at the first 3 eigenvalues and also its corresponding eigenvectors, okay, which can be written here. I select all the rows and the first 3 columns, because first 3 columns will correspond to the first 3 eigenvalues. And analytical solution where n value, okay, I find the first, second and third energy, and then I plot the graph. Okay, that's what I get when a particle is confined in infinite potential well. The first wave function, okay, would be this one, n minus n go to 1. Okay, the fundamental mode, okay, n go to the first overtone and then the second overtone. So you can see that numerical value obtained are quite close with the experimental. Of course, I disagree with discretize with 1000 points, I can increase accuracy by 10 times, and my answer will be very close to the analytical value. Of course, it will take far longer to calculate. Of course, I would not recommend you, and it would take very long to calculate 10,000 points. What I want to show you here is that the wave function, the sign numerical, you need to normalize with np square root dx. Okay, why it is? As you know that in quantum mechanics, all the wave functions need to be normalized to 1. And now we discretize the space into n points, which means that, okay, dx n point, okay, must be equal to 1. However, in a numpy, okay, when you calculate the eigenvalues and eigenvectors, it will return a normalized condition, okay, one single value, but it does not yet account to the discretization of the space. So it is important to divide your answer with a delta x. Okay, so the integral of this one will be the sum of wave function times the delta x. So to normalize it, you make sure that it's equal to 1. So this would be, but in the calculation, this is normalized, so it is delta x. When you calculate the numpy, one single point is normalized, so you have a delta x, so you have to divide the wave function with square root of delta x.